All right, so welcome back to the OneClass channel. Again, my name is Joey. I'm going to be your math teacher for this session. So what's going to happen for this session is that I basically compiled a list of about 10 questions, predominantly from basically, if you're in Ontario, the grade 10 to about the grade 12 math curriculum. So this spans from anywhere between grade 10, 11, advanced functions, and calculus. And if you're tuning in from the US, it's mostly the end of Algebra 1, Algebra 2, and the pre-calculus type of questions. So I have about 10 questions for us for this hour. Don't know if we'll get through all of it, but we will attempt to. Again, if you're here for the first time, thank you so much for watching. What we're doing at OneClass is that we are compiling videos and live streams of teachers verifying solutions to commonly asked questions or frequently asked questions in secondary school level math and chemistry, as well as in the university and college level as well. So again, my name is Joey. I'm currently an Ontario school educator. I'm working for OneClass. And here, my teachable subjects or my subjects of interest are chemistry and mathematics. So without further ado, let's get started on these problems for today, and I'll be able to kind of explain and go through these solutions for you all. So let's get started. So what we have here is our first question here is asking us, what is the limit as x approaches infinity of ln x? So let me write let me write that down for you. So it's asking us what is the limit as x approaches infinity of ln x here. So this is the concept of what a limit is. And if you aren't familiar with what a limit is, it's probably what you would be introduced in about grade 12 calculus in terms of pre-calculus. So when we're talking about limits, as a limit approaches something here. So what we know here is we actually know our we know our function right here. Our function here is ln x here, so it's the natural logarithm of x here. And what this is, the ln of x here, if I were to graph it for you, and you can actually solve this problem by either graphically or kind of using logic as well. But you can think of ln x here as a as kind of a logarithmic function. So what that means is that you kind of get something like so. You kind of get something like this, and it kind of like steadily increases and increases as it heads towards infinity here. So you can think of this here as f of x equals ln x. And if you wanted a better diagram, what you could do is actually, again, I highly encourage desmos.com. And again, it shows you really what this graph looks like. So if I were to type in ln x here, as you can see, this guy here it's going to steadily increase towards when we go towards the right hand side, right? And again, if I were to go towards positive negative infinity, again, this ln can't be 0 here, so there's a little asymptote here that goes all the way down here. So basically, again, we know that the natural logarithm can never be a negative number. So what we're going to do, it's as x approaches infinity here, is going to basically steadily increase here. So when we let me go back here. So basically, here's our function, and it's asking us what is the limit as x approaches infinity. Well, if x approaches infinity here, then my y, where will my y go? My y will also approach infinity, right? If I plug in, use my calculator, ln at e, we know ln e is 1, right? We know ln e is 1, and if you plug in ln let's say ln like 100,000 or something like that, or a very, very big number, you realize that the y value is going to basically increase at a very, very slow pace, but it will still increase here. So this here means that my limit as x approaches infinity here, it doesn't actually approach a specific value. This also approaches infinity here. So it means that in this case here, the limit does not exist for this function here, and it equals, it's approaching basically to infinity here. It doesn't approach a specific number, so this solution is correct. The limit is going to approach infinity, right? So this here, as ln approaches infinity this here, this is also equal to infinity, right? Because again, this y value is going to basically keep increasing, and this will not make it so that it would make it so that it would approach infinity as well. So the limit as the limit of ln x as x approaches infinity equals infinity here. So the solution here is correct, and it's a great analysis as well. again, when we're talking about limits, they either converge to a specific point, a specific y point, let's say 1 or 2 or 3 or whatnot, or it could either be infinite, so it can go towards infinity here, or the limit does not have to exist here. So there's 3 options when we're talking about the limits here. So good solution is correct. Good analysis here. Number 2 is asking us which of the following expressions is equivalent to x cubed minus y cubed here. So I want an expression that is equivalent to basically x cubed minus y cubed. So this here is a this here is kind of a if you know from kind of grade 12 here, this here is our difference of cubes, right? This here is a difference of cubes. Let me write this down here. So here is difference of cubes. And how do you know that? Well, you know that this here is a difference. The subtraction sign is a difference, and the x cubed and the y cubed, both of these terms are cubed. So hence this is called the difference of cubes. And basically for a difference of cubes, it's kind of like a difference of squares, except it's to a higher degree, right? So if you recall, let's see, that if I had x squared minus y squared, I would get x plus y, x minus y, right? And if I factor that, I would get that. So this here would be for a, this guy would have been a difference of squares, right? But now we have one level higher. So this here is a difference of cubes. So what is this? What is this difference of cubes here? So what does this mean? So it means here that if I were to factor, and again, it's a very special case when we have a difference of cubes here. So if I have a difference of cubes here, I'm going to get this general formula. I'll write it in red here. So x cubed minus y cubed. This is going to equal, so I have x minus y, and then so this here is my first term, and the second term I'm going to get basically x squared plus xy plus y squared, and this here will be my kind of general form for the difference of cubes. And there's a really pretty good way to memorize this. If I have a difference of cubes, my first term here, it has to be negative. And this guy here is all positive here. And remember, we know that positive and negative, if I multiply a positive and a negative number, I'm going to get a negative value. So this here is how I would memorize this difference of cubes here. So this solution here, this here is going to match basically either A, B, C, or D. And if we look here, it's going to match basically this D, option D here, right? Because again, I have a negative value here, and 3 terms are all positive here. So option D is correct. So again, my solution here is correct. And you can actually go through and factor all of these guys out to figure out if it was equivalent to x cubed minus y cubed. I believe one of these ones should be a difference of or sum of cubes, and I think it's actually the first guy here. This guy x plus y, and then x squared minus xy plus xy actually gives you a sum of cubes. So this would have been equivalent to x cubed plus y cubed here. So this solution is correct here. So solution is correct. There's good analysis as well. And again, you could always take the long step and actually do you can actually expand the brackets, and then you'll figure out that the only D here is actually the correct answer. So the solution here is correct. Okay, number 3. Asking us why is tangent 0 equals 0? So why is tangent 0? So why is tangent 0 equals 0? So there's actually a lot of ways to solve for this problem here, and actually here the solution that's given to us here is a great way to solve this. So they're basically using a unit circle for us to figure out what the value is. And they're using a quotient identity here. So we know that here tangent, I'll say x here, equals sine x over cos x, right? It's a very, very well-known trig identity here. And if we're saying, and if I have tangent of 0, so tangent of 0, if x here equals 0, isn't it sine 0 over cos 0 here? Which is simply, I know sine 0 equals 0, and cos 0 equals 1, right? Therefore, 0 divided by 1 here is 0. So this is one way of figuring out, using an identity to figure out why tangent 0 equals 0. You can also graph this function. And tangent x is actually kind of an odd graph to graph here, but you get something like this. And then there's an asymptote here, and then it kind of restarts like that. So let me just graph out tangent x here. Tangent x here. So it looks something like this. It's kind of like a little wavy kind of function like I drew here. The first point obviously is 0, 0. And then what we have here, so it's at 0, and then there's an asymptote as it reaches pi over 2, and then it goes back at 0 at pi. So this here is at 0, this here would be a pi, and this asymptote here is pi over 2, and this here is 2 pi. So that's going to be my tangent function, like given at Desmos here. And this here, if I know why is tangent 0, well, add 0 here, the point here is 0. So graphically, you could basically say tangent 0 equals 0 as well. Or we can actually use this unit circle. So there's basically 3 ways to prove this, right? So there's proving this using an identity. This here is through graphing. And obviously, we can also use a unit circle for us to figure this out. And as you can see, they did a unit circle here. They have some type of triangle. So let me draw this out for you because it kind of looks blurry. It might look blurry on your screen here. So I have some type of circle here. And then I have some type of, there's a line here. I don't want that. Sure. And then this here would be again. This here is angle theta, you can say, and then this here would be tangent of theta here. And as the angle here becomes 0, tangent also becomes 0, right? So if I'm looking at this blue guy here, here's my angle. As I'm approaching 0 degrees, right? This here is 0 or 360 degrees here, right? If I'm approaching 0, what is the value of tangent? Well, the value of tangent, this guy here, or let me do this in red. This guy here is also going to become 0, right? Sorry. This here will also become 0. So you can think of this as in 2 ways here. You can think of this as using a unit circle, or actually there's actually 3 ways to think about this problem. Either using a unit circle, or an identity, or you can use a unit graph to figure out y tangent of 0 equals 0 here. So there's a lot of ways for us to support this guy as well. So again, repeating here, this unit circle, as I minimize this angle here, as it approaches 0 degrees, this line here, my y value is also going to diminish to 0 here. So again, this solution is correct. We actually used 3 different ways to prove that tangent 0 equals 0 here. So this solution here is correct. Analysis. I believe that was question 3, I think. Yeah. Question 4 is asking us which function represents the inverse of the function, and we're given that. So I want the inverse of f of x equals 4x. So in order for us to find the inverse, what we're going to have to do is we will actually want to flip this into a y equals kind of function here. When we're looking at the inverse of a function, what does this mean? So let me define this for you. Inverse of a function, I'm going to basically flip x and y. So in order for us to do that, I have to first set this to x, right? Or first set this to y here. So I'm going to say let y equals f of x. So therefore we have this function y equals 4x here. When we say an inverse function, we're going to flip our x and y's. What does that mean? Well, I'm going to do this in blue. I'm going to flip the x and y position. So you can think of this as x is going to be now here, and y is going to be here now. So I flipped both the x and y's here. And what I'm going to do now is I'm going to then isolate for y. And step 2 is isolate for y. And this here will be our inverse function. So how do I do that? Well, I simply have to just divide both sides by 4 to get rid of 4 on the right side here, right? So I'm going to say x here divided by 4 is 4y divided by 4. These 4's cancel obviously. So therefore, I'm left here with x over 4 equals y, or you can say y equals x over 4. And this here is my inverse function here, because this here would now be, and I can represent that using f of -1 of x, and this here is the inverse function equals x over 4. If f of x here equals 4x here, then therefore f of negative x, -1 of x here would equal x over 4. In this case, the notation's bad, and they wrote h of x here, but we can say if h of x here is our inverse function, then we can say simply it's x over 4, and therefore d here is our correct answer. As you can see, they also wrote d as the correct answer, and they basically replaced f of x using y, which is correct. And then they're basically finding the value of x in terms of y. So that's exactly what we're doing in this step here. So we're flipping x and y we're flipping x and y, and then we are basically isolating for a y here. So the solution here is correct. So here's a good analysis as well. Okay, that's number 4. Number 5 is asking, what is the next number in the sequence? So I want the next number in the sequence. And then given the sequence, I have 9, 3, 1, 1 over 3, and then some type of value, and I want the next number, right? So in order for us to look at these sequences and series is kind of the topic of our kind of interest here. So we have in this case we have a sequence here for sure, and we have to either figure out, is this a geometric sequence or a arithmetic sequence? So geometric or arithmetic sequence. And basically in this case here, what we have here is indeed a geometric sequence. And the reason why we have this is because I'm not adding or subtracting numbers as I go through the sequence. Like if you look at only the differences here, 9 minus 3 here is simply just 6, and then 3 minus 1 here is 2, 1 minus here is like 2/3 or something. These guys are not constant, right? So therefore, I don't have an arithmetic sequence in this case. So I would have to have a geometric sequence. And what is a geometric sequence? Well, if I'm multiplying a fixed number from one term to the next here. And in this case, I'm multiplying 9 over 3. 9 times what number would give me 3? Well, I'm multiplying 1/3, right? So these from here to here is also 1/3. Here to here is also 1/3. And we can actually use this. We can basically use a formula of saying what is n2 divided by n1 here to figure out the whatever we call this the kind of our value, and it's going to basically be the proportion, or basically it's going to help us find what the next number of our sequence is. So in order for us to do that, there's a general formula for a geometric sequence, and I'll write this down for you. And it's going to state that a sub n equals a1 times r to the n minus 1 here. And we know in this case our r here is 1/3, right? So we found out that r here equals 1 over 3. So therefore, an n here just means the term here, right? So I can say that this here is going to be our this here is our a1, a2, a3, and a4 here. So I want to figure out what a5 is, right? So if I want to figure out what a5 is, I'm simply putting a5 here. And the n is here equals 5 equals our a. This is our a1 here. And this is it should be a n minus 1 actually. So sorry about this. This is our n minus 1. Actually, this is a1, you're right. This is a1 here. a1 here is 9 times r, which is our 1/3, minus n minus 1 here, which is 5 minus 1 here. And this will help us figure out what this arithmetic sequence is. So a sub 5 is 9 to the power of 1 over 3 to the power of 4 here. And then all I'm going to have to do is use my calculator to figure this out, right? To the power of 4. And this will give us 1 over 9, right? You can think of this, if I didn't have a calculator here, You could think of this as 9 over 1 over 3 to the power 4 would simply just be 1 over 3 to the power 4, right? So power 4 here, 9 times what 3 to the power 4? Well, 3 times 3 is 9, times 3 is 27, times another 3 is 81. So therefore, my last term here, these two guys cancel to make 9. So my term here is 1 over 9. And as you can see, A5 here is just simply 1 over 9. So this here is going to be our answer for this problem here. And again, for arithmetic, for geometric sequences here, they don't really depend on the kind of, it's not a series where they depend on the term that's next to it. They basically, I only need the first term, and I need to find my R value. And once I have those two pieces of information, I can solve for any term in my sequence here. So this here is a 1 over 9 here. So this solution here is correct. Correct. Good analysis here. Number 5. Let's look at number 6 here. Number 6 is asking, find the dimensions of a rectangle with a perimeter of 100 centimeters whose area is as large as possible. Okay, so I'm gonna let me click this link here just so I can see what diagram I get. So give me a second here. I'm gonna bring this up. Okay, so it doesn't actually give me a diagram, so I'm gonna have to draw this out here. So it's asking us, I want to find the dimensions of a rectangle with a perimeter 100 centimeters. So I have P here is 100 centimeters, whose area is as large as possible. A here, I'm gonna have to maximize here. And then I have a rectangle as well. So this problem here, looking at this problem, every time I want to say, I want to maximize or minimize something, this here is an optimization problem. And this here is, I'm going to write here, optimization problem. And every time we have an optimization problem, we have to follow a specific step. So basically what we're going to have to do first is we are going to have to, and this is actually typically seen in a pre-calculus course here. So grade 12 calculus and vectors if you're in Ontario, and pre-calculus if you're in the US here. So in an optimization problem, our first step, what we're gonna have to do is find our formulas, or basically, actually, but even before we do that, let's draw a diagram. And this is actually very, very useful for our diagram here. So I have dimensions of a rectangle with a perimeter of 100 centimeters. So this here, P would equal 100. So I have written down here, and whose area is as large as possible. So I can say here, this here would equal X, and this here is going to equal Y. X here is going to be the length. Y here is going to be our height. And this here, now what we can do is we can actually write an algebraic expression, or write two algebraic expressions for the perimeter, right? So I know that P here is going to equal 2 times X, basically 2x plus y, right? This here is my perimeter of a rectangle formula. I know the perimeter is equal to 100, right? So 100 is going to equal to 100 equals 2x plus y. And what we're gonna have to do with this perimeter here is I'm going to I want to isolate for a variable. And in this case here, let's isolate for y. It doesn't really even matter which one you isolate for. And I'll show you why we have to do that. So I have 2x plus y. I can use distributive property to make this as 2x plus 2y. And then I can simply just divide both sides by 2x. So I would have 100 over 2x here equals 2y. And then 100 over 2x, I can actually simplify. So this is just simply 50 over x over 2y. And then y would equal here. This is simply just 50 divided by 2x, right? And this here, I can even simplify this even further to y here would equal 25 over x. And this here is going to be my first equation that I'm going to have to use to find the dimensions here. So I know that y here is in terms of x here, in terms of our length here. And then what I'm going to have to do now is I'm going to have to start using calculus. So in this case, I'm going to have to write an equation for my area, right? I know that area, I know just right here, I know that area equals length times width, right? So x times y. I know that area is also equal to x times, and then as you can see here, I have y in terms of x, right? I have 25 over x here. So right here, this is 25 over x, right? So this here is kind of our formula for our for our area here. And before we even actually do the derivative here, we can say that here that we can actually cancel these x's out actually. So our area, or what we can do if we want to find the derivative, what we have to do is we actually have to do dA over dx, right? This here is our kind of derivative for of our area in terms of x, and this here you could also do one of two things here. You can actually simplify this guy before we do the derivative, or do the derivative first and simplify after. So because I've already written the derivative, I'm going to do it before after here. So again, I'm using product rule, and I'm simply saying actually let me change this to 25 times x minus 1. It might be a bit easier for us to do our derivatives using this. And let me just double check my work and make sure I have this right as well. So I'm dividing both sides by 2x here. I get 50 over x, which is good. I'm dividing 50 by 2 again to get 50 over 2x. Yes, because I'm doing, give me a second here. Just double check my algebra here. 50 over 2x. I'm just double checking this kind of step here. I'm dividing both sides by 2. So you can simply say I am multiplying by half here. So we get 50 over 2x, which is 25 over x. Okay, that's good. So I'm taking the derivative of this guy here. So if I want to take the derivative here, I'm taking the derivative of the first guy here. So that's of x here, which is simply 1 times 25 over x minus 1 plus, and then I have x here, and we're going to take the derivative of this guy here, right? And the derivative of this guy here is 25 of x minus 1 here is simply just 25 x minus 2 times the derivative of the inside, which is simply just 25, right? So I can, what I can do is now I can simplify our terms here, and what I can do is I can set this guy to 0. So I'm set our derivative to 0 in order for us to maximize our area. I can now multiply 1 in, so I have 25 to the power to x minus 1 plus, and then I have this guy here, which is 25 x times 25 x minus 2, and and this here would equal, I could rewrite this as 1 over 25x plus I have 25x over 25x minus 2. And now what I can do is I can actually cancel these guys out here. So I get 1 over 25x plus x over x, or this is now 2 here, sorry. This is squared, which means I can actually cancel out these guys as well. So I get 1 over 25x plus, this is now simply 1 over x here. And this here is going to equal, again, 0. These guys all equal 0. And what we can do here is we can actually solve for our x value, right? So I'm going to move x to the other side. So we get negative 1 over x equals 1 over 25x. And what I can do here is I can actually cross multiply here. So I have negative 1 times 25x, which is negative 25x. And this will equal x here. And the x's here are going to, in this case here, the x's are actually going to cancel out, right? So this here, what this means is that this here, our length here, or the dimensions of a perimeter whose 100 here is actually 25, right? So this here just means that because I can't, again, these x's here cancel out, which means that the derivative is actually independent of our of these dimensions here. So 25 here is our answer, and as you can see, 25 is going to be our x value for this answer here. So I can basically just I can actually erase this, and I can get for you, let's see, yeah, 1 over x. Yeah, what I could have done here before is I actually could have done, I could actually do x over 1 over 25x, and then, or sorry, 25 over 1 over x, sorry, 25 over x here. I can cancel all these terms here and then take the derivative with respect to 25. And as you can see, the derivative of d over a here of 25 is simply just 1, right? And then 1 here, and if I set to 0 here, this wouldn't exist. So when I were to do dA here, it's going to basically equal 1. And if I set derivative to 1 here, this is no good, right? The math is no good here, so, which means the derivative is basically independent of that. So basically what I'm saying is that the area here is simply 25, or it's actually, the dimensions here is actually going to be equal to 25 here. So it's actually independent of our derivative here. So I can basically say, therefore, x here is going to be 25. And then all I'm going to have to do is, I'll have to do is sub this x here back into one of these our area formulas here to get our or I can sub it back to our perimeter to get our formula, our y value, sorry. So I have p here equals 2x plus y. I know that this here is 100, is 2 times 25 plus y here. Oh. And then all I'm doing here is 100 equals, using FOIL, 2 times 25 is 50 plus 2y. 100 minus 50 here is simply just 50 over 2y. Y here is going to equal 25. So therefore the dimensions for the largest area, so therefore you can say dimensions of rectangle with p equals 100 centimeters is 25 centimeters by 25 centimeters will give us our maximum area of this case here, So this solution here is correct, 25 by 25, although they did not show any work here. So the solution is correct. Poor analysis because no work is shown, but logic is correct. The logic is there. So the solution here is correct. Okay, what number was that? That was number 6 here. So again, with all of these maximization problems, you have to basically you have two formulas you're gonna have to use, and you have to isolate for a variable, and then sub that variable into the other formula, and then take the derivative and set it to 0 to isolate for one variable. So it's a combination of actually a lot of things in optimization, which is the tricky part of that. So number 7 is asking us if f of x is, so if f of x here is 3x plus 2, and if g of x is x squared plus 1, find the value of f of g of x. So this is here is our composite f of g of x, and hence it's and find, so I want f of g of x, and I want the domain, and I want value at x equals -2. Okay, so I have a lot of things to do here. So I'm going to label this here. I want to do the first part, the second part, the third part here. So let's do our first part here. First part is asking us, what's f of g of x? And this here is a composite function, right? This here is our composite function, where basically we want to put, it's going to basically mean this is f of g of x. So basically it's a function within a function here. So how do I do that? Well, I have f of g of x here, so I have g of x is equal to this guy here. So x squared plus 1 is g of x here. And I'm going to take f of g of x here. So the f of g of x will be 3x plus 2 here is going to be subbed into this function here. So I can say that, actually let me erase this here. So I have f of x. I'm going to sub my g of x for x here. So I have 3 times, and then this x is going to be x squared plus 1. So x squared plus 1, and this is plus 2 here. So this here is my f of g of x. So this is the composite function that I'm looking for. And I'm just going to clean this up by saying that this here is simply f of g of x is going to equal, I could use FOIL again, so this is 3x squared plus 3x plus 2. And this here is going to be my f of g of x. So this here, sorry, this is not 3. This here is just simply just 3. I don't know where I put my 3x. Sorry, this is simply just 3 plus 2, and f of g of x is going to equal 3x squared plus 5. And this here is our function for f of g of x. Number 2 is asking for our domain, right? So our domain of this function. So what is the domain of f of g of x here? And our domain, if you look at this this function here, is 3x squared plus 5. This here is a parabola, right? So you can think of this function as a parabola. My leading coefficient is above 1, so you can think of this as some type of function that's opening. Oh, it's going to open upwards, right? It's going to open upwards like this. And it wouldn't open downwards like so because I don't have a negative value. Again, this isn't actually 3x squared plus 5 here. If I really wanted to graph this function here, I could basically grab the x-intercepts, solve for the y-intercept, and so on and so forth. I think the y-intercept is actually 5 in this case here. But I wouldn't do that for this problem. But either way, we care about the domain of the parabola, right? The domain of the parabola means that I know that my d here, my domain of this function here is x, belongs to a set of real numbers. And why does it belong to a set of real numbers? Well, I don't have any limitations to my x, right? If I go all the way to negative infinity and to positive infinity here, I still have a y value. It's still defined for 3x squared plus 5 here. So the domain of this function is simply x belongs to a set of real numbers, and there are no restrictions to this domain. And I want to find the value at -2, right? So I want to find the negative value, or the value at -2. So step 3 now. Step 3 is I want to find x at -2 of this function here. So I'm basically writing here, this is going to be f of g of x equals 3x squared plus 5. And I want to sub in x minus 2, right? So this is going to equal f3 times -2 squared plus 5. This will equal -2 squared here is 4 plus 5. 3 times 4 here is 12 plus 5. Which will equal 17. And this here is going to be my answer for this problem. And as you can see, it's 17 as well. So the composition function is correct. Domain of f of g of x is a collection of all real numbers. So x belongs to a set of all real numbers, which is good. And x at -2 is 17. So the solution here is correct. Great, good analysis as well. Okay, what number was that? Number 7. Number 8 is asking us, how do you get cotangent, cosecant, secant on my calculator? Okay. So this is more so a trigonometric ratio, right? This is number 8, I believe. Is this number 8 or number 7? I believe I did number 7. Yeah, this is number 8. Oh, what did I do? How did I do that? How did I do that? Oh, sorry. Number 8 here is asking, I want to get these following functions. I want cotangent, cosecant, and secant. So how do I get these guys? Because they don't belong in my calculator, right? So right now I'm currently using a Casio FX991, and basically you're not in a calculator. You're actually not given these ratios. What you have to do is actually know the reciprocal ratios for us to figure out our functions here. So let me write something down first. Let me write down a table here. So again, I know that I have sine x here, I have cos x, and then I have tangent x here. These guys are my primary, actually, let me do a chart for you. I think it's a lot easier if I do a chart. Do a little t-chart here. Actually, wait, can I redo one of these guys? Yeah. Let's see, let's do something like that. Okay, so I have a t-chart here, and basically I have a list of, these are primary trig ratios, and this here is a secondary, or this here would be the, not a secondary, but this here would be a reciprocal trig ratio. So for example, I have sine theta, I have cos theta. Again, theta is just an angle, right? Tangent of theta here. The reciprocal would be of sine here would be cosecant of theta. Reciprocal of cosine is secant of theta, and tangent here is cotangent of theta. And what does that equal to? Well, if it's just a reciprocal, it's a 1 over our primary trig ratio. So this here is actually 1 over sine theta. This here is a 1 over cos theta. This here is 1 over tangent theta. And these guys here are my reciprocal trig ratios. And we can't actually use these, we can't actually plug them into a calculator, but all you're gonna have to do under calculator is simply just plug in 1 divided by, and then our primary trig ratio as well. So this solution is correct because they're doing 1 over tangent of A, which is cotangent, 1 over sine of A, which is cosecant, and 1 over secant here is cosine, 1 over cosine here. So the solution here is correct. And again, what they did was they wrote it out exactly how I did as well. So cosecant of A here is sine A, secant of A here is cos A, and then cotangent of A here is 1 over tangent A as well. So the solution is correct. Good analysis. So this is what you would plug in into your calculator. Let me highlight this in blue. These guys here are going to be plugged into your calculator here. Okay, number 9. How do you simplify ln of half? I want to simplify ln of 1 over 2. Okay, so this here, because again, ln here is our natural logarithm, right? Ln here is our natural logarithm. And if it's a natural logarithm, it actually follows all the logarithmic rules, right? So we know that. So there's a couple of logarithmic rules you need to know before we jump into this. So I'm going to use log first, and it's not ln, but I'll use log first. So if I have log of xy here, it's going to equal the log of x plus the log of y. And then if I have log of x divided by y here, I know it's log of x minus log of y. So for log here, if this is this is the logarithm here, I have a natural logarithm also follows these rules, right? So ln of x times y is ln x plus ln y, and ln of x divided by y is ln x minus ln y here. So knowing this rule, what we can do is we can actually solve for this guy here, right? So let me do this in blue. So if ln of 1 over 2 is going to equal ln of x here, which is simply the ln of 1 minus the ln of y here, which is ln of 2, right? And we know ln of 1 here. The ln of 1 here is indeed 0, right? So this case here, this would be 0 minus ln 2. So therefore, if I want to simplify ln of half here, this is simply just negative ln 2 here. And this here is our solution for this problem here. And you can actually plug in ln 2 if you want to figure out your the decimal place here. If I were to get that, I would get here, this is negative 0.69315. And this here is our correct solution for number 9 here. And this solution here is correct. So again, this solution is correct because they use the logarithmic rule as well. Solution is correct. Good analysis. And then number 10. Number 10 here. Okay, so this is another optimization question. So it says a square sheet of cardboard of side length A is used to make an open box by cutting equal squares from 4 corners of sides and folding up the sides. What size squares in terms of A should be cut out of the corners to obtain a box of maximum possible volume? What is the maximum possible volume in terms of A? Show all work and justification in your solution here. So I don't know if they give you a diagram here again, because this is actually pretty hard to visualize. I hope they do. Let me just check here. So they don't actually. So that sucks. But what I can do is, I don't know if I have enough time to actually explain this. And again, the solution is definitely incorrect here because I don't see any solutions here. There's no numbers here. But what I can do here is I can actually solve for, let me draw this out for you first. So I have some sort of square sheet. I'm making an open box, right? So this is going to be a box in 3 dimensions here. So let me just draw out my box. and it's actually an open box. So this top cover here is open, right? And I know that for a box here, I have a volume, and I want a volume here. A volume. So the volume of a box is simply just, I can use it's x times y times z, right? And this here, or a times b times c, it doesn't really matter what you kind of use. In this case, I use a, b, and c. So let me use a, b, and c here, where it's a, b, and then this here is c here. Doesn't really matter. It's just the product of those things. And again, this is the volume of a rectangular prism here, and this is going to equal, again, a minus 2x here. So a minus 2b, and then times a minus 2b times x here. So they used a different kind of a notation here, and they changed it up because, again, it says I want a side length of a, right? So my volume is going to equal a minus, I would say, I guess this is 2b, a minus 2b times b here. And then this here is going to be, I can use this to help me figure out my volume here. And what I'm going to have to do is I'm going to have to first, I need to isolate for one variable. Right now, currently, I have two variables that I have to work with. So, well, actually, what I have here is, I can isolate for a variable here for me to figure out, so I can plug this back into the, so I can actually do the derivative of this. So it says here differentiate at x equals minimum. So at x equals, basically if it's less than 0, thus maximum volume. So the solution here is, the logic is here, right? Because again, I'm basically taking the derivative of this volume and I'm setting it to 0, and I'm figuring out when is the function going to be negative. That will be my maximum volume here. So if I were to solve this problem, I would basically, let me FOIL this first. So I would get a squared minus 2b minus 2b, 2ba, sorry. No, this is minus 2ba minus 2ba. So this is minus 4ba plus 2b squared times b here. And this here is going to equal, I have a squared b minus 4b squared a, or actually 4ab squared plus 2b cubed here. And this here is our volume, right? And what I'm going to have to do is I'm going to actually take the derivative in respect to one of these variables here. And again, I don't have, and I want to find out the volume in terms of a, right? So basically, I'm going to take the derivative of d over v over db here, and this will give me a volume that is respected to a, right? Because again, I'm looking at what size squares in terms of a should be cut out of the corners to obtain a box of maximal possible volume, and it says what is the maximum possible volume in terms of a here. So again, I'm taking the derivative in respect to b. So again, this guy here is simply just a squared. This here would be, again, I would again, 4a's are all the constants, right? So I don't have to worry about these guys here. This 2 is going to be brought down, so I'm going to have 2 times 4a here, which is 8a times b here. And then I'm going to have, for this guy here, is I have 3, I'm going to bring this down. I'm going to have 6 here. 3 times 2 is 6. And then this would be simply b squared here. And then I would basically set this guy to 0 to figure out the maximum volume here. So this here, I would set this to 0, and then I would have a squared, or let me see, 6b squared minus 8ab plus a squared here. And then in this case, what I would have to do is I would have to actually I would factor in terms of b here to try to figure out if I have to figure out basically something in terms of b here. So in terms of the dimensions here. So this here would give me, if I were to solve for this this quadratic here. Again, this is simply a quadratic, right? Because I know that a here is a constant. So a is always a constant here. So basically, I would basically plug this into my my quadratic formula to figure out what my possible dimensions are in terms of a here. So this solution, so this is, I believe, all the work I can do for this problem here. And yeah, I think that's about it for this problem. Maybe I'll see if I can factor. I don't know if I can factor 6 times. Again, this number is a constant, right? So I don't know if I can actually factor this guy here. Because again, I have a squared here, so this here is a constant. But I could common factor these two guys out, but I don't think it's going to help me out here that much. I have a b here that's common, so I have 6b minus 8a plus 8 squared. It's not actually going to help me a lot. So basically for this problem here is I have to basically now turn a into a fixed variable. So assign some number of a here to complete my quadratic equation here, so I can solve for this. So this here would be very, very similar to something that's ax squared plus bx plus c, and then I would have to assign some type of number of a to solve for this solution here. So again, this is all the work I can do for this this kind of problem here. And I can't verify my solution because the solution here is obviously incomplete. But this here is what I would be given if I were to set the derivative and take the derivative in terms of dv over db to get me this formula here. And I set it to 0 to maximize the volume again. So again, another differentiation problem. So I'm going to say the solution is incomplete here. And then I'm going to say here what I got was, I got v here would equal basically a squared times b minus 4ab squared plus 2b cubed. And then if I get dv over db would equal, this is a squared minus 8ab plus 6b squared. And then I can basically set this to 0 equals. I'm going to copy and paste these guys here. 6b squared. And yeah, that's all I can do with this problem here. Yeah, and setting derivative to 0 would maximize the volume. So I'm going to say solution here is incorrect because it's an incomplete solution here. This was number 10 here. And finally, number 11, finish it off in about a couple minutes here. It says define the reflection rule for the points in the xy plane across the x-axis here. So again, if I have some type of, so what they did with the solution here is that, for the sake of time, I'm just going to skip to my solution here. But what they're going to do is they're going to reflect a specific point here, right? So I'm reflecting across the x-axis here. So if I had some type of function here, and the best example is to actually use a quadratic here. So if I have a quadratic function, we all know that this here is y equals x squared, and this here is the x-axis, this is the y-axis, right? If I want to reflect this and I wanted to make this reflection happen, I would get something like this, right? I would reflect this along this axis here, and this guy here would be y here equals negative x squared. What I'm doing here is I'm changing my a value, right? This is a positive a value, which is 1. So a would equal 1 here, the a here equal to negative 1, right? So if I want a reflection rule for the points in the xy plane across the xy axis, all I'm going to have to do is change the sign of my a variable. So if I had I have a function here, and this is for any function. So I can say maybe, let's see, y here is going to equal a times f of x minus b, or minus b, or sorry, bx minus b, or minus c, plus d here. And this here is basically a general formula for any of these functions here. And for example, in this case here, f of x is x squared, right? So simply I have y equals a times x squared, right? In this case here, my a was equal to 1. So we get this top formula here. If I want a reflection along the x-axis, I would make a here to -1, right? So this here would be -1, and I would get this bottom guy here. So if I want a rule, I'm simply just changing the sign of my a value here to reflect a function along the x and y axis here. So this solution here says reflection point rule for, oh, it's a point. Sorry, this is a point for an x and y axis. I did it for a function, but this here would actually be the same thing as well. And all I'm doing for a point, if I were to specify a point, let's say, so this is actually like more complicated because I'm reflecting an entire function here. Let's say, for example, I know a point here. This is here's 1, 1. If I were to reflect it along the x-axis here, this one would, the x-axis wouldn't change, or x wouldn't change, but the y value changes, right? So this would be -1 instead. So this here, I'm going from AB to A comma -B, and this here is a great solution for reflection of a point. I went one step further and I actually reflected the entire function here. So solution is correct. Good analysis as well. So with that, that brings me to the end of my video. Again, thank you so much for watching this live stream. Again, my name is Joey, and I stream math from basically Monday, Wednesdays, and Fridays. And I stream chemistry on Tuesdays and Thursdays. So you can come check me out then. If you like these videos, definitely check out our YouTube channel at youtube.com/OneClass, and you can find all our recorded videos and our live streams on that site as well. And as always, thank you so much for watching. Stay safe, stay healthy. Have a great day. Take care.